One of the key determinants of what type of data model that we want to work with is the type of phenomena that we're looking at. Broadly speaking, we can have two different types of phenomena, either discrete or continuous. So discrete phenomena are objects that are distinct with well-defined boundaries. They're countable, so there's some finite number of them, and their geography or their boundaries can be exactly measured. So you can very exactly measure the perimeter of a building or the center line of a road or the point location of a tree. Continuous fields lack clearly defined boundaries, so they can be measured at essentially an infinite number of points, and values can vary pretty dramatically over short distances. So a common example in GIS is elevation, for instance. Building on that, discrete phenomena, the data can only take a set or limited number of values. So that's things like land cover or zoning classes. Whereas continuous data, measurements can take any value within some range. So for instance, temperature can be 10 degrees or 10.1 degrees or 10.11. There's essentially an infinite number of different values within some range or space that the data can take. Now, vector and raster data can both be used to represent continuous and discrete data. Generally speaking, raster is better for continuous and vector is better for discrete, but there are some applications where, due to certain circumstances, you might want to use one or the other. So continuous phenomena vary across space, and the cell values can correspond to values that were measured or estimated at a certain location. A good example of a raster data set that is continuous would be sea surface temperature anomalies. So these are measured by satellites that are rotating around the Earth and capturing the information at specific points where it's sampling the sea surface temperature, and it's using a grid of cells to represent the values across space. But raster data can also represent discrete entities, so these are sometimes called thematic rasters. And this is where the value is discrete, so it can only take a set number of values, but it's continuous over space. So a good example is land cover. Everywhere within a certain range has a land cover type, but there's only a discrete number of land cover types. So agriculture, deciduous, pine trees, etc. So even though it's continuous across space, the actual values themselves are discrete. Looking at the vector data model, discrete entities are uniform objects with defined boundaries. So roads or buildings, they're all one type of object and they can be represented using a certain layer. Whereas continuous data can also be represented with vector data. A good example would be contour lines, so like on a topographic map. So you use lines, which themselves are discrete entities, to represent a continuous phenomena across space. So this can be useful for aesthetic purposes or for navigation, but it's not necessarily particularly meaningful for geospatial analysis. If you want to analyze something having to do with elevation, typically you want to use a raster data model instead. Now, things are rarely as cut and dry as discrete or continuous. If you take a snapshot in time, maybe something is going to be discrete or continuous, but often it falls somewhere between. So we call these things vague or fuzzy objects. And so a good example would be the Aral Sea, which at one point in the 1960s was the fourth largest inland body of water in the world. But due to poor water management practices, the sea has shrank to just a fraction of its current size. And you can see just in this 14-year time slice, there's dramatic variability in the size of this body of water. So how do you represent the Aral Sea? Is it a discrete or a continuous object? It's not really either. It varies through space and time. And so some choice comes into play when you actually try to represent this on a map. What boundary do you use? If you use the outline from the 1960s, which you can see here on this map, you're going to be very, very wrong. Whereas if you use the low water level in 2009 to represent the data in 2010, where the lake rebounds a bit, you'll also be quite wrong. So we have to think about how do we draw lines around features with fuzzy boundaries. Another good example might be vegetation on a hill slope or a mountainside. So we have this transition from barren land at the very top down to alpine, mixed, and then forest, and then grass. But where does the boundary between grassland and forest start? Is it where you hit the first tree, or is it where the trees become, or the tree canopy becomes more dense than the grass, or is it not until there's full coverage of tree canopy? The choice might depend on what exactly you're trying to do. Another key consideration is the map scale. And so this is the relationship between the distance on a map and distance in the real world. So how much smaller than reality is the map? So the scale itself is an attribute or an entity associated with the map you are making. What level do you want to look at? And then there's a related concept called resolution, which is actually an attribute of the data, and I'll talk about that in just a minute. So the map scale is essentially how much smaller than reality is the map. So we can represent that in a couple different ways. There's the graphic scale using a scale bar, which you did in lab 1. There's a verbal scale, so you can say 1 centimeter on the map equals 1 kilometer in the real world, or you can use a representative fraction, so 1 to 100,000, which means that 1 unit on the map is equal to 100,000 units in the real world. And you'll get a little bit of practice with this in lab 2. So as counterintuitive as this sounds, a small scale map is really zoomed out and it's showing a really large area. It's showing the whole world, for instance. Whereas a large scale map is really zoomed in and it's showing a small area. So this might not make so much sense. It might seem backwards, but if you think about it, referencing the representative fraction, for instance, a scale of 1 to 1,000 is essentially a fraction, 1 over 1,000. And so that's a really small scale map because 1 divided by 100,000 is a really small number. Whereas a large scale map might be like 1 to 100, where 1 unit on a map represents 100 units in the real world. And so that would be a relatively speaking larger fraction because 1 divided by 100 is a lot larger than 1 divided by 100,000. So this large scale, small scale map is a really tough one to get your head around. It still trips me up to this day, but it's important to consider the scale of the map that you're working with. So just to kind of drive it home, another look. Small scale map might be all of Western North America, whereas a large scale map might be just the west end of Vancouver. So again, small scale is zoomed out. It shows fewer details. It's more generalized. And so you can see the representative fraction here. This is a 1 to 10 million scale. It's a very small number, whereas the larger scale on the map is more zoomed in. Shows a lot more detail for a smaller area. And so there's got to be a lot less generalization. And so the representative fraction for this map is 1 to 1,000. And you can see when you represent that in fraction form, it ends up being a lot larger of a number. So the scale of the map is going to determine how general we can be with our data. So all maps require some simplification of real-world features because the real world is essentially infinitely complex. And so whenever we draw a map, by definition, we are creating an abstraction representing some simplified form. But if we are zoomed way out and we're doing a small-scale map, then we can have a lot more generalization than if we're zoomed way in and doing a large-scale map. So for example, if we're looking at the Mississippi River, what scale are we looking at the river? If we're looking at it 1 to 20 million scale, that's the continental US, then you can just use a squiggly little line to represent the river. If we're looking at it at the 1 to 5 million scale, you might have to add the other rivers that are coming in because we need a bit more detail to represent the object at this scale. 1 to 250,000 scale, you might not be able to represent the river as a line anymore, and instead you have to represent the river as an area. And you might have to represent the bends and the oxbow lakes and things like that. And if you do 1 to 500,000, you've got a really zoomed in version of the map. You might even have to represent different features within the channel, like sandbars, features along the shoreline of the river, like buildings or docks or things like that. And so the difference in scale really is going to govern how much information we need to include, how general we can be, how we have to look at